All right, let's go ahead and start. So today we'll talk about quantum data compression. So I want a dedicated lecture to that. It's a very important theorem in quantum information theory. We're going to do it in a way that I haven't seen presented before. So, okay. Let's also call the Schumacher compression. Schumacher invented this protocol, and he invented the word qubit, which is now, of course, very famous. So we quantified the units of quantum information is qubits, right? So there's the physical qubit, but there's also the information qubit, and that's what we're going to talk about today. Okay. So quantum compression. Schumacher. I believe it's German for shoemaker. Okay, so we're just going to get right into it. We're first going to talk about a one-shot version of a quantum data compression protocol, and then we'll consider the IID case kind of as like a special case. Okay, that's actually how we did Stein's lemma. We did not do Shannon data compression like that, but it's an interesting perspective. So we'll start with one-shot data compression protocol. Okay. And what we imagine is, classically, what was the central object of data compression? It was the information source. It was a probability distribution that describes the source. And so here, the generalization of a probability distribution is a density operator. Okay? So a quantum information source we'll imagine as simply being a density operator. There are other ways to describe quantum data compression in terms of an ensemble. Okay? Like the ensemble where when you mix the pure states, you get a mixed state, but we're just going to do it this way. The difference, I suppose, is in the interpretation. So yes, I'll speak about that. So give it as a density operator with a purification. Let's first talk about this, and then we'll come to the ensemble interpretation. So with a purification, phi rho on R and A. So rho will be a density operator on system A. Okay. And what does a general protocol look like? It looks like this. So there's going to be a sender and receiver. Although with data compression, it doesn't, you don't have to necessarily think of it that way. You could just think that sender and receiver are just one person, and the sender is doing the compression into a smaller number of qubits than the source is represented. Okay. So there's a source that generates the purification phi rho on systems R and A. Okay. The reference system is not available. Right? And sender does an encoding or a compression channel. Okay, so it's just some channel, and then we'll call this system W. That gets sent over an identity channel. If it has dimension, the dimension of this is. Just to note like this, mod W. So the number of qubits we're compression into is log base 2 of mod W, right? Log of the dimension is always number of qubits. Okay, and then the receiver does a decompression. Technically, if we're doing sender and receiver, then we should draw a dotted line. So the receiver does a decoding or decompression. And the goal is to reconstruct the system such that now we can use the metrics that we talked about, right? The ideal thing is that you reproduce the state exactly. That would be a zero error compression protocol. Okay? But what we do is we follow Shannon, we allow for a slight error. Okay? We allow for a slight error. And then if we allow an error, we need an error metric. The error metric we'll use is fidelity. That's a one-shot measure of performance that has an operational meaning for how well this state could pass a test for being the original state. So that's the formulation that Schumacher came up with. There's another one called the Ensemble interpretation.
What is idea? Sorry.
We're going to write it down. So the protocol is, there's two parameters we'll focus on for now. W epsilon protocol if fidelity between phi rho RA and phi rho RA, then the encoding acting on A going to W composed with the decoding going from W to A hat. So if this fidelity is greater than 1 epsilon, then it's called a W epsilon protocol. And then the operational quantity of interest is called the one-shot data compression limit. Quantum data compression limit. Okay, so we'll call that QDL. It's a name. So QDL epsilon of rho. So it's a function of epsilon and rho. Take a minimization over all possible encodings and decodings and registers W. Log base 2 of the dimension W. Let's call this equation here star, this inequality, fidelity greater than 1 epsilon, right? And then it's just simply that such that star holds. Right? That's the operational quantity. Right? So that's one version of quantum data compression. So that's clear?
There is no epsilon in the multiplying the log to or something. You don't get penalized by having epsilon bigger.
This is how we formulate it. So fix an epsilon, fix a rho, subject to that constraint, try to make the size as small as possible. Right? And so that's one way of thinking about it. Another way of doing it, which we won't do, is you fix epsilon. You fix W and you try to make epsilon as small as possible. Right? That's another kind of operational task. It's related, but this is the way we're going to do it. Question.
So the 1 that's the compression check.
That's the metric of performance, right? So the goal is there's a source state, there's a state produced by the source, okay? And then this sender and this receiver are trying to compress, this might be 10 qubits, and then they might be able to compress it into 2 qubits, right? As an example. And so it gets compressed to a smaller system. This is just some arbitrary channel. And then it gets transmitted over an identity quantum channel, dimension W. And since you can think that identity channels are expensive, right? So you try to minimize, make it as small as possible. Quantum memories are expensive. In some sense, they don't really exist. You know, it's debatable. And then there's this decoding to take as an example, we said 2 qubits back to a 10 qubit system. And then we want the state at the end. It's going to be generally some mixed state to have fidelity larger than 1 minus epsilon with the original state. Okay? Yeah.
What's the point of the identity?
All right.
It's all the same.
I just drew a box. You like the box or don't like the box?
The point is that it's not so easy to have.
Yeah, I just want to say like that's the resource that we're trying to minimize. Yeah, that's like the expensive resource. I'm gonna put it there.
Seems trivial if it's not, but it's not.
Yeah, it's the thing you're trying to minimize. Okay, so that's the task, that's the goal. I want to take you back to possibly day 2 of this class, right? And I want to remind you of the basic idea behind data compression. Okay? So previously we talked about this for the one-shot case, and we had a probability distribution. I think we had this discussion before we went to the IIT case. Okay? So with the density operator, it is a spectral decomposition. And lo and behold, what do you have? A probability distribution. Okay? So organize on a histogram the probabilities from largest to smallest. Right? Okay. So let me make this slightly larger. So the source is an 8-level source, right? An dimension 8 source. Okay. And suppose 3 qubits, right? Dimension 8, 3 qubits. Suppose that the total probability mass of these symbols together is less than epsilon, right? Then what will be the idea of data compression? You would simply project onto this subspace, right? You can divide these symbols. Let's do this. Let's call this set like the typical set, and this the complement, right? So then you can rewrite this decomposition. You can divide it into 2, right? Okay. And then what is the idea behind quantum data compression? It's going to be precisely the same idea as classical, except now project onto a subspace. Right? Previously, we asked the question, is the symbol typical or not? That was the key thing for classical data compression. How do we ask a quantum question? We do a projective measurement. We do a yes/no measurement. Right? So then quantum data compression will be this. This is the very basic idea. We're going to do a bunch of math to justify some things, but this is the basic idea. So IT will be the projection onto this subspace, and ITC will be identity minus that, or the projection onto these. Right? So that's going to be the basic idea of quantum data compression. We assume that there's knowledge of what the density operator is, and then with that knowledge, you're allowed to form this measurement. So you can offline like compute what is the high probability subspace, and the scheme for compression will be first measure onto the typical subspace, right? Do this typical subspace measurement. If you get the outcome, no, not typical, throw away, right? Just like forget it, it's gone. made an error, but it's not too large, right? And then if you get the outcome, yes, typical, you do an isometry to rotate you from a space of an 8-level system or 3 qubits to a 2-qubit or 4-level system. Okay, so that's what the encoding will do. You send it over 2 qubit channels. It's not an isometry. Its dagger is an isometry, but you could call it a compression.
Okay.
And I believe that that's the formal mathematical term for it. Yeah, but it does exactly this quantum data compression. And then the the dagger of it is an isometry, and that's what you do for the decoding. That's it. That's the basic idea.
How do you know what is a typical set?
You know the density operator. We assume in quantum Shannon theory that you have unbounded computational resources available, okay, for the basic theory. And then, given the description of the density operator, you can simply calculate what is the typical subspace. You can line up the probabilities from largest to smallest, and then do exactly this.
In a practical application?
In a practical application, you need to design actual data compression codes. And then for the classical case, there are all kinds of compression schemes. In fact, you can teach an entire class on that. And then there are some works on quantum Huffman codes. It could be interesting to do more work on quantum data compression. People are now doing quantum machine learning. There's something called the variational autoencoder, and it tries to learn through like a variational quantum circuit what is this high probability subspace. So that might be interesting as a presentation for someone to talk about the quantum variational autoencoder. Okay, that's the basic idea. What is the ensemble formulation of this? Let me speak to this briefly. So your source could be like this. And you can imagine that this is now a classical system, okay, that identifies the letter Z. Right? So we can imagine this as a classical quantum state. Okay. And then locally, when you trace out the reference, you realize a density operator. It's the mixture of, you write it like this. So the information source could realize this density operator, and these need not be orthogonal. But then when you take the spectral decomposition, you would get this. Okay? And then the goal would be precisely the same. To look at this fidelity, where R is a classical system. And then due to properties of fidelity, it will look like an average fidelity, where the average is with respect to this distribution. Okay?
I don't really appreciate the difference with the
The difference is the interpretation of the density operator. Is a density operator an ensemble of pure states, or is it one share of a purified pure state? That's the difference. But it turns out if you can do quantum data compression according to this criterion, you can do quantum data compression when R is classical. Okay? And that simply follows from data processing and something called quantum steering. Any ensemble, okay, so suppose that, let's go back to here. Something called quantum steering that Schrodinger discovered in 1935. Suppose you have the density operator on system A, and you have a purification. Okay? And then suppose this density operator can be realized as this complex combination of the pure states in the ensemble. Okay? Someone who has the reference system can do a measurement to realize this ensemble, such that the outcome Z occurs with probability P of Z, and the state psi Z is realized. Okay? And that's the basic reason why quantum data compression, according to this criterion, implies quantum data compression when R is classical. If you're looking at this thing, this fidelity is non-decreasing under a measurement channel that realizes this theorem. Okay? So that's quantum data compression. And now I want to define the asymptotic form. We're going to stick with the original formulation. So I want to define these asymptotic quantities. First will be the quantum data compression limit, right? And you take the one-shot quantity and you take limits. It's basically you write down, you evaluate this quantity, one-shot one, but with rho tensor n, right? And you put in a tensor product of states. But similar to what we did with Shannon's theorem, we looked at an IID distribution. Normalized by the number of symbols. So now this is a rate. Number of qubits per source symbol. That's the data compression rate. Okay. And then what you do is you take limits. Limit as n goes to infinity, limit as epsilon goes to 0. You can make it very precisely formulated with lim sup and supremum. And then this is a very precisely defined quantity that always exists. Remember, like a limit need not necessarily exist, right? But then lim sup, lim inf always exists, right? So this is like you're being pessimistic for data compression. That you're taking a lim sup rather than a lim inf. Okay? And there's a strong converse quantity. We'll put this as 2dl with the tilde on top, and this is where you just flip the primo to infimo. Okay. And then same thing here. Over it. Okay. The way you think about this intuitively is it's saying like there exists a sequence of data compression codes such that the rate converges to this limit, and the error of the scheme is also tending to 0. But for any finite n, we're allowing for a slight error. And then we demand that the error vanish asymptotically. Okay. If you want to make this simpler, then you can. This is the kind of thing people will do when they give a research talk. They say, "Oh, 2dl rho is lim epsilon going to 0, lim n going to infinity." And then there's like, this limit may not necessarily exist, where this is like precisely operationally defined. Okay. Because supremum is always larger than femum, we have that QDL rho is greater than QDL rho. Yeah. But what the data compression theorem shows is that this is actually an equality. This is due to Schumacher, and the strong converse is from one of our former very eminent lecturers, Andreas Winter, who did it during his graduate studies. So it shows that you have an equality. Both of these are equal to the entropy, von Neumann entropy of rho. So that's the fundamental operational meaning of von Neumann entropy as data compression limit. Okay. So if you want to interpret this, the way to interpret this is with this kind of diagram. This is to be interpreted in the n infinity limit. Okay. So here's infidelity. Right, so infidelity is 1 minus fidelity. Here's rate. And here I'll put the entropy. Right. Okay. So the theorem, another way to interpret the theorem is that if you're above the data compression limit, you know, if you're not trying to cram everything into too few qubits, then you can do so without error. Okay, so for any rate above this, error is 0. Strong converse says that as soon as you cross that data compression limit, as soon as you're trying to cram everything into too few qubits, and the n infinity limit, the error jumps up. The error infidelity jumps up to 1. Right? These are all supposed to be 1. All right, just try to squiggle to make it very clear. Okay? So then that's saying that if the rate of data compression is below this limit, then for every possible scheme you could ever come up with, you will fail, guaranteed, at the task of data compression. Okay? I don't know. Maybe there's some kind of analogy with like cramming for exams. There's only so much information the brain can store. So like the exam comes with probability 1. Yeah.
Is it supposed to be obvious that the
This is not obvious. This is the goal of today.
Oh,
To prove this. Yeah. This is by no means obvious. I would say none of this is obvious. Okay. So the goal, and we do have 50 minutes, is to prove both sides. So the goal of today is, this always holds. So the goal for today is to show this upper bound and this lower bound. Okay? We use different techniques to show them. Okay. For this inequality, this is the main concept. This is the main concept. Okay. For this inequality, we need to use data processing. Okay. So the previous textbook, things were done with typical subspaces, right? And this was done with data processing of mutual information. Okay. Now we're going to try everything with Renyi style. Right? And then you get some interesting one-shot bands as well to do things Renyi style. Okay, so the goal is to talk about this first and then this. Any questions before we proceed? All right. I think, yeah, we have to kind of kill some of this stuff. We'll probably reproduce this figure and then you have this in your mind. Okay, so we have the density operator rho, the spectral decomposition like this. And then remember, we're going to be bounding this quantity from above, the one-shot data compression level. That's going to be called the achievability part. We exhibit some scheme that can, we give an upper bound on this quantity. Right. So for this quantity, we have to fix epsilon. Right, so fix, this is the error tolerance we're allowing, some number between 0 and 1. All right, and then we're going to let pi, this is going to be the pi t that we wrote previously. We're going to call it pi epsilon a. That's going to be the projection onto the high probability subspace of rho. So we have projection satisfying such that, you know, if you were to do a measurement according to this projection and its complement, probability of getting this outcome is larger than 1 minus epsilon. So most of the probability is there. Okay. And we will write it. It'll be in this basis, you know, so it's collecting the eigenvectors with the largest eigenvalues. We'll call this set T, or typical. Okay. M will be the size of this subspace. Actually, that's what we should call. Actually, that figure. Why don't I reproduce it in small form? Okay, so the size of this subspace will be trace of the projector, right? Projector has eigenvalues 1, and so if you take this trace, you're just counting up the size of the subspace, rank of the projector. Okay, and now we're going to introduce. Okay, we're going to make another observation. If we perform this projection on one share of the purification of rho, RA, and just from property of partial trace, right? This evaluates to trace over R, and then this is equal to this. Okay? Those are equal just from using partial trace. You have identity on R. Okay? So this is greater than 1 minus epsilon. That's an observation we need. The next observation is not so trivial. So we take log base 2 of W. The claim is that this is greater than, remember this hypothesis testing relative entropy, right? So that's the claim. Why is that true? Before justifying this, let me remind you of something. So entropy of rho is equal to minus relative entropy to the identity operator. Okay, you can use definitions to arrive at that. And then we knew from Stein's lemma that, like, you know, if you evaluate this, you know, as and goes to infinity, this converges to relative entropy. You can kind of see where we're going with this by connecting with hypothesis testing relative entropy. Okay. For the IID case, and you plug in identity for the second argument and a minus sign, you recover entropy. Okay. So why is this true? I'm going to write out this definition. So log themum over all measurement operators. This here is a measurement operator. Okay. All measurement operators lambda trace of lambda subject to the constraint that trace of lambda rho is greater than 1 minus epsilon. That's straight from the definition. Okay. So why is this inequality true? Well, this is an example of a measurement operator, right? It satisfies this constraint, it satisfies this constraint right here, right? And then this involves an infimum of the trace. Well, the trace is W. And, you know, this is an example that fits into this. And that's why you get this inequality. Okay. All right. So, okay. There's an inequality that goes in the other direction. And it has to do with the fact that the dimension of a system has to be an integer. Okay. So like, we can rewrite this inequality. Let me rewrite this slightly, saying that W to the minus VH epsilon. Okay. So it's like W is, you can think of this as saying W is the smallest integer that can satisfy this inequality. This is like a real number in front of the smallest integer. The claim I'm making now is that there's a lower bound on this. That. Okay. You know, any real number can be sandwiched by one integer and an adjacent one, right? So that's basically all I'm saying. All right. It turns out this is the one that we're going to need. Okay. So now let's talk about what is the E and the D? What is the E and the D? The encoding and decoding, the compression and the decompression channels. What will those be? Okay, so E will essentially be a channel version of what we said. Okay, so it's like the first part you do the ask, is it typical? If so, compress. This U will be a compression map. Why don't I write down the U now? The U it's going to be over the elements in the typical subspace. Take the element X, right, the eigenvector X, and you map it to an element of a smaller subspace. So we'll call that W of X. Okay? And W of X is, so every element X in the typical subspace gets mapped to a unique element of the system W, right? You know, if we were to have this histogram that we had previously, we could enumerate them as like A, B, C, D, E, F, G, H, and this would be X in T, the typical subspace. These are the X and T. This would get mapped to 1, 2, 3, 4, for example. These could be the W of X, right? So that's the compression. Okay. This is not yet a channel. We need to complete it to a channel. We can need a little more space. So then what do we do if it's not typical? Well, we just discard the state and replace it with something in the subspace, something in the typical subspace, in the system W. Right? So that will just be, you get this other outcome. Yeah, sorry. Sigma W. Just some state in the W that acts in the W Hilbert space. So that's the encoding. What is the decoding? So then, this encoding happens. It's a legitimate channel, right? It's a compression channel. W gets sent over an identity channel. What is the decompression? Well, it's just going to be inverted, right? But it has to be a channel. That's the nodes. Yeah. Actually, I made it more complicated than it needs to be in the nodes. I'll change that. So the decompression will just be U A to W. Okay. Flip it. This, when you flip it, it becomes a map from W to A. And that is what's in isometry, going from the smaller space to the larger space. Then what happens when you compose these? When you compose these channels, we can go through some of the math operator qualities. But I'll just show you what happens is that you can prove that this is a state that's larger in the operator interval sense than the typically projected state. Let's see what we find. Okay. So then you can show, you just kind of like work through the element. What does that mean for fidelity? Well, this is the fidelity we're looking at, right? So fidelity this one is a pure state. Yeah, question.
I don't understand why that's equal instead of greater than.
You want it to be equal?
Yeah.
Or you're curious why it's not equal? Because you have this other stuff. That's the essential reason. Yeah, that's the essential reason. Actually, yeah, that is the argument. Like you act with this on this, you throw away this term, which is positive semi-definite, and then this inverts that, and you're left with that. So that's the argument. I'm glad we did it, because it's actually, I don't know why I skipped it. Because in my notes, I had something more complicated. Okay. Fidelity of a pure state with a mixed state. There's a simpler formula for that. We talked about it. There's a sandwich of this by Roth by ket phi. And now we can apply this operator inequality. This, remember, this right here is a shorthand for ket phi draw phi. So this actually is the square of this. Right, absolute value, but this actually is a real number. Right? Technically, we could this. And then this expression is the same. You know, we can use, we can put a trace over the whole thing, use simplicity of trace, and then it ends up being the same as this. Right? So this is the same as trace identity R I squared, and then that we know is greater than 1 minus epsilon squared, and then I'm going to write this out as 1 minus epsilon 2 minus epsilon. Then we're going to keep all these terms. So what have we done? We have, let's look at the definition of the one-shot data compression limit. You have defined an encoder and a decoder such that the star holds, and make this as small as possible. Okay. So what have we done? Let's summarize what we've done. We've shown encoder, decoder, such that the fidelity criterion is satisfied with this error, epsilon times 2 minus epsilon. We're going to shortly fix that to be just epsilon. Such that W is less than this quantity plus 1. This quantity plus 1. Right? So then what does that mean using definitions? The quantum data compression limit has an infima over all of them. So we showed some examples. Right? So then we get an upper bound. We have to take a log, right? On this too. This plus 1 is a little annoying, but it has to be there. So what we have done is, since we've exhibited an encoder with this error, sorry, a data compression scheme with this error, and such that the number of qubits that we're compressing into satisfies this inequality. We've now shown that log base 2 minus dh epsilon plus 1 is greater than QDL epsilon 2 minus epsilon. Right. That's what we've shown. Okay. It's more desirable to have the error written as epsilon. What we can do is invert this function. Right? And the inverse of the function, there's a unique inverse of this function on the interval 0 to 1. So we consult the node. You can also say that QDL epsilon rho is less than log base 2. I'm going to put an epsilon prime here. Epsilon prime equals 1 minus root 1 minus epsilon. That's the inverse of this function on the interval 0 to 1. Yeah. Yeah. Yeah, sorry, that was slightly confusing. This was the epsilon we chose for typicality. What happens is that in this bound, we don't get 1 minus epsilon. We get 1 minus epsilon squared. Yeah, I mean, maybe I should have switched all these epsilons to deltas or something like that. But I think you follow what I'm saying. So indeed, the definition had epsilon, and then we said fix epsilon for typicality. And at the very end, we did a switch of what epsilon meant, such that epsilon now refers to compression error. Yeah.
Why did you have to take the inverse of epsilon to the
Not the inverse of epsilon, the inverse of this function. Right? So it's like, I forget what the functions look like. But, you know, if we define this, I forget what it looks like, but I'm just going to make some guess. I don't know, whatever, you know, something like this. Okay, whatever, just plot it, and then it's the inverse of this function. Yeah. Why? Because we wanted the operational quantity to have the error epsilon, not the information quantity. Okay? So you could think of what we were doing here was this is an operational quantity where the error should be epsilon, and then we gave this upper bound and something in terms of something that's more like an information quantity, functional graph. However, you could argue back to me and say the dh epsilon is an operational quantity, but then this we know how to connect to Renyi's. Okay, that's our next plan. All right. Okay. Right. So, any questions about like what happened from a conceptual perspective? So, I mean, I think the conceptual part is summarized in this plot. I keep the high probability stuff. And the rest of it was like, all right, let's construct the explicit channels. So this is a channel, this is a channel. And then we use the fact that we chose a high probability subspace. This is what appears in Fidelity. So then we connect with this to get a statement that, oh, well, if we choose a high probability subspace for data compression, then indeed the protocol will have a small error. So that's what's going on. Okay. So now let's recover the von Neumann edge. This one. Okay, so there was an inequality we used previously to connect hypothesis testing relative entropy to Petzreni. So let me first rewrite this slightly. Rewrite the inequality we got as we'll take power of 2. 2 to the log cancels 2 to the q to the log. We'll make it easier. 2 to the QDL epsilon rho less than minus pH epsilon prime. Rho. Okay, so previously we had this inequality that allows us to connect hypothesis testing to Petzreni. We used it in the context of the Stein's law. We didn't prove it. We left that something in the book that you can look up and study. And we'll do the same today. So this holds for all epsilon between 0 and 1 and alpha between 0 and 1. Okay. Then using the definition of Renyi relative entropy, this is the same as minus H alpha rho minus alpha 1 minus alpha. Okay. So this inequality, do you remember this from the Stein's lemma? It was probably like 2 weeks ago, 3 weeks ago. All right. There's some. It's an important inequality. There's a section in the book called the connections between hypothesis testing and Renyi relative entropy. The focus of it is to get this balance. All right. So now that we have that, we can apply it and say that 2 QDL epsilon rho less than epsilon prime. And so there's this plus 1. So what I'm going to do now is just make the bound much more loose. And yeah, this quantity here is always greater than 0. That means this is greater than 1. So we're just going to do 2 times. It'll make things a bit easier. Okay. And then now it's kind of just take long. Okay? That's 1. Log base 2 is 1. All right. This is the fundamental one-shot bound. Right? So this holds for all alpha between 0 and 1 and epsilon between 0 and 1. Okay. And then now what we're going to do is we're going to try to get the asymptotic. We erase the definition of the asymptotic quantities. So, but now the calculation we'll do is essentially some basic steps that were similar to what we did in Stein's law. Okay. So we plug in tensor power state. That's going to the asymptotic case. So, okay. What about this quantity? What is this simplified to? Yeah, many entropy is additive for tensor power, tensor product states. Then we just get H alpha, and then plus all this other stuff. Okay. So then now we apply the definitions, right? Definition was lim sup, sup of epsilon. We take the limit as n goes to infinity. This stuff that depends on the error goes away. Right? Same thing that happened with Stein's law. So now applying definitions. So alpha rho. This bound is a uniform bound holding for all alpha between 0 and 1. Right? So now, since it holds for all alpha between 0 and 1, take the limit as alpha goes to 1. The Renyi entropy, remember we said that the Renyi relative entropes are monotone alpha, monotone increase. The Renyi entropies, they have the minus sign in front, right? So they're monotone decreasing. So as alpha approaches 1, they get smaller. Right? Remember, alpha 0, that's the rank, the log of the rank of the state, the number of physical qubits in the state. Okay? But then taking the limit as alpha goes to 1 gives you the number of information qubits. Okay? In the Schumacher sense of quantum data compression. Now, limit 1 is less than H rho. Okay, and then that's the upper bound. That's the upper bound. So what you saw happen was we had this basic idea of let's generalize Shannon's data compression scheme in some way for the quantum case, and then we did all these like entropy tricks to get to this statement for the asymptotic case. Okay, so that's the achievability part. We have 15 minutes. I think we could do the converse. So the converse, I'll I'm going to write a final implication. Final implication that the asymptotic quantity QDL will less than the 1 million entropy. That's the completion of the achievability part for the asymptotic case. Okay, what about the converse? That will involve studying this diagram, coming up with an interesting information quantity and using data processing. Okay? So the quantity that we'll use, perhaps not so intuitively, other than the fact that it's something that obeys data processing, we'll use mutual information. Okay? Maybe I'll give you a sense of why we're going to use mutual information. So we look at mutual information of a pure state phi. Remember, that's the entropy of R, the reduced state on system R, the reduced state plus the entropy on the reduced state on system A, minus the joint entropy. Right? For a pure state, the joint entropy is 0. And also, the marginal entropies are equal to each other. That was some facts that we did. And so this is actually equal to twice the entropy. So that's a good, if we have a hunch, which we do, that the ultimate data rate is entropy, then using mutual information, because it has its feature, is a good idea. Okay, we're trying to do everything Renyi style. So we're going to use Renyi mutual information. Right? And then I'm going to state a bunch of facts, and we're not going to prove them. Actually, some of these facts are not in the book. They're in a research paper that I collaborated with some others back in 2015. Okay? I'll give you the reference. So we use Renyi mutual information. Bipartite state. I'm going to use the system C and D to define everything so that we don't confuse with A and B and A hat. All right, so the Renyi mutual information will depend on a parameter alpha, mutual information between the system C and D, the state rho, so it's like a correlation measure, right? And we'll define it this way. Taking an enum over states of the D system and the sandwiched Renyi relative entropy. So one thing I want to remind you of is if here, rather than sandwich Renyi, we use quantum relative entropy, the standard one, then we compute this, we'll actually get the quantum mutual information, the standard quantum mutual information. Okay. So that this formula looks like that. And then what is the sandwich Renyi? Let's remind about that. In states omega and tau. It's this one. It's one quantum generalization of the classical concept. Right. So what are the properties of this? This is where I'm going to point you to a paper. First is a dimension band. Okay, so for a finite dimensional system, Renyi mutual information is limited by the dimension of D. Twice D. This is a limited range of alpha, for alpha between 1/2 and infinity. The other key thing, so this is what's going to allow us to connect to the dimension of the compression system. That's what we're trying to band, right? The goal of what we're doing now is to get a kind of like a lower bound, state of compression. What's an accomplished part. Okay, so data processing on the local channels. there's a channel that goes from T to C prime and D to D prime. Right. So that just, what does that say? Correlations cannot increase under local processing. Right? This local processing can only reduce the correlations or maintain them. That's what it says. The local processing for us will be this encoder decoder. We're going to be looking at each information here and track how it progresses through the circuit. All right. The other thing we need is something we call pseudo continuity. What is this? We need different parameter data. If you have two states, rho and sigma, of the system C and D, we want a statement of like, well, how close are the Renyi-Mitchell information? Okay? And the bound we can give is a lower, and this suffices for what we need. Lower bounds in terms of fidelity. Okay? Also, all fidelity, rho CD, sigma CD. This holds for alpha between 1/2 and 1, and then beta is related to alpha by this formula. So, definition of the quantity, dimension bound, data processing in local channels, pseudo continuity. We need one more thing that's like this. The Renyi-Mitchell information related to entropy. So let me write that down. That is in the book with Sumit. It's this. So for a pure state psi, this becomes twice H 1/2 alpha minus 1. Entropy in the system state. Right? So this generalizes this formula. You recover this one by taking the limit as alpha goes to 1. Right? As alpha goes to 1, well, this converges to this, and this converges to H1, which is von Neumann entropy. Okay, those are the things we need. Now that we have it, 5 minutes left. I think we can do it. Possibly. All right, so let's do it. First thing first, we're going to consider an arbitrary. Any possible W epsilon data compression protocol. Right? We want to relate the dimension of the protocol to the error and some information function of graph. That's the point. So let's start with the dimension. Let's call this state here sigma. Let's call this state here omega. This is system W. So first thing, dimension. 2 log W. And we want to do it right here. Mutual information between R and W. And then we want beta. So alpha will be it's a number between 1/2 and 1. if beta will be this number. That's fine, right? We're sort of like pattern matching with this formula. We're replacing D with W and C with R. Right? Now what? So we've related dimension to an information measure here. Okay? Then under the local processing, the information measure goes down. So data processing, R and A hat. The final state omega. Okay. What do we know about the final state omega? We said this is a W epsilon protocol. So the error is no larger than epsilon. That means that final state here is a fidelity larger than 1 minus epsilon with this state here. Okay. So now we want to use the pseudo continuity bound. Use this one. And we're going to use it with respect to the initial state, because that's the guarantee of this fidelity question. Right? This state right here is omega, an R and A hat, and then for an arbitrary W epsilon protocol, it's guaranteed to satisfy this constraint with the fidelity. So I want to connect to it, and we're using this inequality, and then we're bringing it to the upside. So plus alpha 1 minus alpha log fidelity between phi RA and omega RA. Okay. And this holds for alpha between 1/2 and 1. That's the range we're using. What does that mean? This is a positive number, right? Log is a monotone function. It's a W epsilon protocol, so we can use the fact that fidelity is larger than 1 minus epsilon. Ah, I forgot to do alpha. Alpha. We're going to do two things. We're going to apply this equality to get Renyi entropy. Remember, this phi is a pure state at the beginning. So we can use this to write Renyi entropy. And now you see we've connected to entropy. Connected the size of the system to entropy. 2H. I'm going to just call it rho because that's the reduced state. You trace over R, you get rho A. Right? Just call it H. And then the upper bound comes, this was an equality. The upper bound comes about, I'm going to put 1 minus epsilon. Using the fact that fidelity is larger than 1 minus epsilon. That's the fundamental one-shot bound. Fundamental one-shot converse bound. So what is it saying? For an arbitrary data compression protocol, let's do one more rewrite. I'm just going to divide by itself. What is it saying? An arbitrary W epsilon protocol, we proved using this properties of information measures that number of qubits you're trying to compress into has to satisfy this inequality for all alpha between 0 and between 1/2 and 1. Okay. What do we have on the right-hand side? An entropy measure function only of the information source, and then the error nice and cleanly separated out of it. Okay? So since this inequality is uniform, holding for all such protocols, this implies that it'll hold for the smallest possible dimension you could put. That's QDL. Right? And what do we use data processing? So we're 2 minutes over time. The rest of it is similar to what we did before, right? To get the asymptotic case. This was the one-shot found. To do the rest of it, I'll just state it now, and it's like the mirror of what we did a few minutes ago, right? Plug in row tensor n, divide by n. Plug it in here, divide by n. Entropy is additive, so then you don't have the n there. Then you have divide by n here. Take the limit as n goes to infinity. This stays there. This goes away. Right? This holds for all alpha between 1 1/2 and 1. Take the limit as alpha goes to 1. Now it's getting larger. Is that right? With its inverse, yes, it's getting larger. From below, it's getting larger. Right? So you'll then get von Neumann entropy is a lower bound on the asymptotic quantity, independent of epsilon. And then you get the lower bound. So all of this, let's just summarize it. QDL, strong converse, greater than h of k. So, we've now shown a sandwich. So altogether, what did we show today? We showed the achievability part greater than the data compression limit. Data compression limit, by definition, is greater than the strong converse one. And then now with the converse, we showed no, the match. So it all collapses, you get equality. Good. Not sure what the plan will be for Monday.